Chapter 17 is about expected value and standard error. So for our first example, suppose you flip a fair coin 100 times. How many heads do you expect to get? If it's a fair coin and you flip it 100 times, then you would expect to get half heads. So you would expect to get 50 heads. So the question is, will you actually get this number every time? No, you don't get 50 heads every time you flip a coin 100 times. You're going to get about 50 heads, but not exactly. And it's actually going to change every time. So for number 3, let's now find a box model for the number of heads. So for our box model, we're flipping the coin 100 times. So because we're doing 100 times, it's going to be the sum of 100 draws from the box. Okay. And then what goes in the box? We're counting the number of heads. Remember, anytime you want to count, when you're making your box, you just have two numbers, a 1 and a 0. The 1 will represent our heads, the 0 represents our tails, and because heads and tails are equally likely, we just need 1 1 and 1 0. So when we flip our coin 100 times, we don't actually always get the exact number of heads that we expect to get, and we call it the observed value as the number of heads that we actually get. The observed value differs from the expected value by some amount of chance error. And the standard error, which we're going to abbreviate as SE, gives us the likely size of our chance error. So the standard error tells us how much our observed value is likely to be different from our expected value. So for this example, let's think about drawing 25 times with replacement from the box 0, 2, 3, 4, and 6. So here's one set of 25 draws, so I just randomly drew out 25 numbers, and I got a 6, then a 0, 4, etc. And the sum, when I was done, was 66. Here's another draw. Now I got a 0 first, then a 3, then a 2, and a sum of 61. And another draw, I got a sum of 62. Notice that my sums were changing each time. And in fact, I can take many samples of size 25 and look at the sum of the draws. So I had a sum of 84, 78, 71, 66, 62, 85, 86, 79, 81, 80, etc. Once again, notice what's happening here. The sum of the 25 draws changes each time we do it. So not only do the actual numbers that we draw out change, but the sum changes. And in fact, I could program the computer to draw 25 times with replacement from this box. And I had the computer do it 100 times, and here are the resulting sums. So I had 71, 76, 86, etc. up to 62. So the computer drew it out 25 times, and it did that 100 times. And it's easier to look at in a histogram. So these represent the actual sums of our 25 draws. So, did we get the same sum every time? Well, no. We got things like an 84, a 58, an 80, an 82, an 88. We got different numbers every time. Now, does there seem to be any pattern to the sums? It does seem to be a little bit of a pattern, right? Like most of our numbers are kind of there between like 70 to 80. The bulk is kind of 75 to 80. Sorry, the numbers are shifted quite a bit. So we could say most are from 75 to 80. Okay, what else do you notice when you look at this? You might notice that it kind of looks like a normal curve. So the actual sums of our 25 draws is a data set. So just like any other data set, we might be interested in measuring the center and the spread for all the sums. So for these 100 sums, the average is 73.26 and the standard deviation is 9.14. Now I found a different set of 100 sums and it had an average of 74.5 and a standard deviation of 8.9. So not only do the sums change when we do it, but if we do it 100 times, then we do it a different 100 times, we might even get different averages and standard deviations. So now some theory. We have expected value and standard error. Expected value, we're going to abbreviate this with an EV with a little sum, tells us that the average of the sum of the draws. The standard error, SE sum, tells us the standard deviation of the sum of the draws. So if we repeat our 25 draws many times, so if we do this many times, we're talking hundreds, thousands, hundreds of thousands times, we expect the sum of the draws to be around the expected value with the standard deviation equal to the SE sum. And as a note, our observed values are rarely more than 2 or 3 standard errors away from the expected value. As a final remark, in general, we use standard deviation when we want to find the SD of a list of numbers, but we use the word standard error when we're talking about a chance process. So how can we find the expected value in standard error? The expected value for the sum of the draws is going to be the number of draws times the average of the box. And the standard error for the sum of the draws is going to be the square root of the number of draws times the standard deviation of the box. And we're going to find the average and standard deviation of the box with the calculator, okay, or Excel, or throughout all of your homework I'm going to go ahead and tell it to you to save time. So for example 170, think about drawing 25 times with replacement from this box. So we have the numbers 0, 2, 3, 4, and 6. Number 1, we want to find the average and standard deviation of the box using a calculator. So instead of using a calculator, since I'm on the computer, let's go ahead and use Excel. So to use Excel, say I want to find the average first. So I'm going to do equals average and select my numbers. So my average is 3. Now for the standard deviation, I'm going to do equals standard deviation. Notice that there's 2 standard deviations, a P and an S. And you'll notice that on the notes I said use the one with the P. Select your numbers. And so the standard deviation is 2. So the average for the box is 3. And the standard deviation for the box is 2. Again, we're just using a calculator. There's no reason to do this by hand. If you did want to do it by hand, you'd go back to chapter 4 and use those formulas. Number 2, find the expected value for the sum. The formula for expected value for the sum is equal to the number of draws times the average of the box. So number of draws, how many draws do we have? We're drawing 25 times. So it's going to be 25 times the average of the box, which is 3. So my expected sum is 75. Now for the standard error, that's going to be the square root of the number of draws times the standard deviation of the box. So this is going to be the square root of 25 times the standard deviation of the box, which is 2. This gives me 10. So we found the expected value and the standard error. What does this tell us? What is this useful for? Okay, so there's 2 ways you can interpret this. So first is if we repeat the 25 draws many times, we'd expect the sum of the draws to be around 75 and the standard deviation to be about 10. Or another way to say this is that the sum of the draws is likely to be around 75 because it's always likely to be around the expected value for the sum, give or take 10 or so. So again, this is what we're going to talk about over and over. So the sum of the draws is going to be likely to be around the expected value for the sum, give or take the standard error for the sum. So the reason why is that the standard error of the sum tells you what you can expect the size of your chance of error to be. Or in other words, the standard error for the sum tells you how much you're likely to be off from what you expect. So we expect to be off by about 10. Now I used my computer to take many samples of size 25 and I looked at the sum of the draws. So if I did it 10 times, the sums had an average of 73.3 and a standard deviation of 7.7. For 100 times we had our average of 74.5 and a standard deviation of 8.9. For 1,000 times we had an average of 75 and a standard deviation of 9.7. And 10,000 times the average is 75 and the standard deviation is 10. So the more times we repeated these 25 draws, the closer the actual averages, so my observed averages and standard deviations, get to the expected values of my expected value for the sum and my standard error for the sum. So again, the more times I do the sum, the closer the average and standard deviation get to my expected value and standard error. In our next example, we want to play a game in which we roll a 6-sided die 10 times, and we get paid the amount shown on the die each time. How much do you expect to win in total? Give or take how much? Notice on this one that I've given you the average for the box and the standard deviation for the box. This is just to save you time when you're working on your homework or the test. I'll do the same thing. I'll tell you the average and standard deviation of the box. So number one, find the box model for your total winnings. Let's see, so we're rolling the die 10 times. So it's going to be the sum of 10 draws from the box. And what needs to go into the box? You roll the die and you get paid the amount shown on the die. So the amounts you can have are 1, 2, 3, 4, 5, 6. So after you roll the die 10 times, you just add up all of your winnings to find the total. So now let's find the expected value for the sum. The expected value for the sum is equal to the number of draws times the average of the box. So there are 10 draws times the average of our box, which is 3.5. Again, remember I told you the average and standard deviation. So this gives me 35. Find the SE for the sum. SE of the sum is equal to the square root of the number of draws times the standard deviation of the box. So it's going to be equal to the square root of 10 times the standard deviation, which is 1.71. This gives me 5.41. So I have my expected value and standard error, but again, what does this really tell me? This tells me that I expect to win a total of about $35, give or take $5.41. Because we know that we're not very likely to win exactly $35, but it should be about $35, give or take $5.41. So example 173 is very similar, but now let's say we're going to roll our die 100 times, and we get paid the amount shown on the die each time. how much do you expect to win in total, give or take how much. So again, we have our average and standard deviation. Notice those are the same as in our last problem because we're still rolling the six-sided die. Okay, number one, find the expected value of the sum. So expected value of the sum is equal to the number of draws times the average of the box. Number of draws, we're doing it 100 times, so 100 times the average of 3.5, so 350. Now for the standard error of the sum, it's going to be the square root of the number of draws times the standard deviation of the box. So the square root of 100 times our 1.71 gives me 17.1. So we expect to win about $350, give or take $17.1. What does give or take mean? So we could say then we expect to win about, so if we do 350 minus 17.1, so 350 minus 17.1, it gives us $332.90 to, and then if we do 350 plus 17.1, it gives us $367.10. So it kind of gives us a range of likely values for how much we'll win. Now this is still an about. We're not guaranteeing that you're inside that range, just that that's the most likely range. Now, up to this point, I've been giving you the standard deviation and average of the box by hand, or saying that I did it from the computer. But there is a way, if your box only has two different numbers in it, a big number and a small one, then there's an easy shortcut to find the standard deviation of the box. And if that's the case, you may as well do it by hand. We just don't want to do it by hand when there's more than two numbers because it takes a long time. So if you only have two different numbers and they can be repeated, then the standard deviation of the box is equal to the big number minus the small number times the square root of the fraction of numbers that are the big numbers times the fraction of tickets with the small number. So for example, you play a game in which you roll a die 10 times. Each time a 6 occurs, you win $10. Otherwise, you lose $1. How much do you expect to win, and give or take how much? So first, I have told you what the calculator, average, and standard deviation are, but we're going to do it by hand. So first, before you can do that, you need to know what actually goes in your box. So let's find our box model for our total winnings. So we're rolling a die 10 times, so it's going to be the sum of 10 draws from the box. Let's see what goes in our box. Okay, if you roll a 6, you win $10. Otherwise, you lose $1. Notice those are our only two options. You either win $1 or you lose $1. But how many of each of those tickets do we need in there? There's only one 6 to get you $10, so there's only one ticket for the 6. But there's 5 other numbers that make you lose, the 1, 2, 3, 4, and 5. So there's 5 tickets to let you lose $1. So that's our box model. Now we can find the average of the box and the standard deviation of the box by hand. So to find the average of the box, how do you find the average of the box? You add up all the numbers and divide by how many numbers there are. So there's 110 plus my next number is a -1 and a -1 and a -1 and a -1 and a -1, because remember we had 5 -1s, 5 tickets with a -1. Divide by how many numbers there are? There are 6 numbers. So don't forget that even though we only wrote down 2 numbers, there were really 6 different tickets in there. So you have to write out all of the numbers. And when we put that in our calculator, we're going to get 0.83. Now for the standard deviation of the box. So once again, it's going to be our big number minus our small number times the square root of the fraction of the big number times the fraction with the small number. So what does this give us? When we say big number, we just mean $10 is the bigger number. So 10 is the big number, -1 is the small number. So it's going to be 10 minus our -1 times the square root. So when we say the fraction of the big number, we mean how many of these tickets have the big number. So there's only one that has the big number of 10, but there's 6 total tickets. So 1/6 of the tickets have the big number. Times now the fraction of the small number. So the small number is this -1, and there were 5 out of a total of 6 tickets that had that number. So times 5, 6. Put this in your calculator. Don't forget your parentheses around the 10 minus -1, or your parentheses around 1/6 times 5, 6. And this gives us 4.1. So once again, 10 was the big number, -1 was the small number. Now that we found the average and standard deviation of the box by hand, we can find the expected value for the sum and standard error for the sum. So expected value for the sum is equal to the number of draws times the average of the box. So number of draws, we're doing this 10 times, so there are 10 draws, times the average of the box, which is 0.83, so 8.3. The standard error of the sum is equal to the square root of the number of draws times the standard deviation of the box, which is equal to the square root of 10 times the standard deviation of the box. So this gives me 13. So what does this actually mean for us? We expect to win about $8.30, give or take $13 or so. So sometimes I'll even write that in. So give or take $13 or so. Because again, this isn't exact. We might be $10 under or maybe $15 over. This is just kind of a estimate of how big our chance error is likely to be. Example 175, a multiple choice test has 20 questions, each with 4 possible choices. Each correct answer is worth 5 points, and for each incorrect answer you lose 2 points. If you guess all the answers, what do you expect your test score to be? Give or take how much? And once again, I've given you the calculated values for the average and standard deviation in the box, but we're actually going to find these by hand. So the first step is to write down the box model. So your test score is like the sum of how many draws. So it's 20 questions. It's like you're doing this 20 times. So 20 draws from the box. Okay. And then what goes into the box? Let's see. Each one has 4 possible choices. Each correct answer is worth 5 points, and for each incorrect answer you lose 2 points. So I assume there's only one correct possible choice, and so there's one answer that's going to give you 5 points. The other answers are going to give you negative 2 points each. So there's one correct answer and 3 incorrect answers that each give you negative 2 points. Now, because it says if you guess all the answers, what do you expect your test score to be? So if we're just guessing all of our answers, we're equally likely to get any one of these tickets, and so we can just do one ticket of each. Now let's find the average and standard deviation of the box by hand. So average of the box, you just add up the numbers on the ticket. So 5 plus negative 2 plus negative 2 plus negative 2, and divide by how many numbers are there. Are 4 numbers there. So this gives me negative 0.25. So if you're just guessing, the average for one question is that you'd be losing a quarter of a point. And the standard deviation of the box, notice how there's only 2 different numbers in the box, either 5 or negative 2. So we can use our shortcut here, which is big number minus small number times the square root of the fraction with the big number times the fraction with the small number. And by this is the fraction of the tickets. So big number, 5 is the bigger number. So 5 minus a negative 2 times the square root. So fraction with the big number, there's 1 5 out of a total of 4, so 1/4. Times, now the fraction with the small number, there are 3 tickets that have the negative 2, so 3/4. Put this in your calculator. Don't forget to put parentheses inside the square root. And we get 3.03. So this is the average and standard deviation of the box. Remember, the box itself represents just one trial, or in this case, just one question. So it's saying if you answer just one question by guessing, the average score would be about negative 0.25, and the standard deviation would be 3.03. Now for the sum, it's saying now we're doing this 20 times and going to add up our results. So let's find the expected value of the sum. So our formula, once again, is number of draws times the average of the box. Number of draws, we had 20 questions, so it's 20 draws. Average of the box is negative 0.25, so this gives me negative 5. And the standard error of the sum is equal to the square root of the number of draws times the standard deviation of the box. So square root for the number of draws, square root of 20. Standard deviation of the box, we just barely calculated that to be 3.03. So this gives me 13.5. So what does this truly mean for us? It means we expect our test score to be about negative 5, because the expected value for the sum is negative 5, give or take 13.5 points. So this means if you just guess, you are likely to get between, so if we do negative 5 minus 13.5, it would be negative 18.5, and if we do negative 5 plus 13.5, we get 8.5 points. So if you just blindly guess, you're likely to get a score somewhere between negative 18.5 and 8.5 points. Notice that that's a big range, and the reason why is that our standard error was so big, which comes back to our standard deviation of the box was so big.